All right, guys, so in this section, we're going to continue along with exponential growth and decay. When you guys first look at these notes, it might look a ton different from what we've already been doing, but you're quickly going to realize it's basically the exact same thing that we learned about in 7.5. Okay, all this is like a different way to break down that equation we learned about earlier. Okay, so the first thing we're going to throw at you guys is an equation that models specifically exponential growth. Okay, and what you might be thinking to yourself is, wait, Mr. P, I already thought we learned the equation for exponential growth and decay. And you're exactly right. It was that formula, y is equal to a times b raised to the x power. Okay, this equation models both exponential growth and decay. But what we're going to show you guys today is basically just like a different way to break down this equation up here if you know you're dealing with growth. Okay, so let's compare this equation to this guy up here. It looks pretty similar, there's just a few extra pieces. So when we're dealing with exponential growth, it's typically going to be a word problem. We just got to know what each of these variables can represent. So the first thing we see on the left is a y equals, just like we see up here. So y is always going to represent like we call the final amount. When we're dealing with exponential growth, we know the amount of whatever we're looking at is growing over time. If what we're trying to solve for is going to be that ultimate, the final amount after a certain amount of time has passed. So y equals is still the left-hand side of the equation. Okay. After the y equals, we still see an a in both these equations. And what you need to know about a is what we call the initial amount. Okay. The amount that we're starting with, whether it's number of people or cost, whatever we're looking at, a is the starting amount based on whatever time they're giving us. Okay. But the key difference here is that instead of calling my number in parentheses b, we're going to break it down to two different pieces. There's going to be a 1, and then we're going to add r. Okay. Whenever you're dealing with exponential growth, you can break down this number b or this letter b into two different pieces. It's always going to start with a 1, and then we're going to add what we call the rate of change. Okay, the rate of change is the rate at which the expression is increasing, the rate at which it's growing. Okay, what you need to know about rate is that the rate is usually given as a percentage. But when we're doing exponential growth and decay, we have to convert these percentages to decimals. Okay, one of the most common mistakes is you guys forget to do this. But when you're searching for these pieces in the word problem, our first step is we have to convert the rate percentage into a decimal. Okay, so all we did is we just broke down that number inside parentheses into its two separate pieces. And then the last difference is that instead of calling it to the x power, we're calling it to the t power. Okay, but t represents time. Okay, it's no different than the letter x. Okay, so here's a scenario. It says a college's tuition has risen 5% each year from the year 2000. 5% each year since 2000. And it says if the tuition in 2000 was $10,850, tuition in 2000 was $10,850, write an equation for the amount of tuition t years after 2000. Okay, the first thing we have to do is we have to write an equation, and then after that we have to predict the cost of the tuition in 2015. Okay, so first, let's write the equation. In this example, we're talking about college tuition. College tuition is getting more expensive every year. More specifically, it's growing at 5%. It's getting 5% more expensive every year, so it's going up and up. Because we know it's going up and up, this is going to be the exponential growth equation. We know it's going to follow the format y equals a times 1 plus r raised to the t power. Okay, so now all we have to do is we have to pull out the key piece of information from this question and plug it into this formula. Okay, so we want our equation to solve for the final cost. We don't know what that is yet. We're going to call it y equals. Okay, a always represents your initial amount or your starting amount. Okay, so in this question, they're telling us in the year 2000, which is the first year we know about, the cost was $10,850. Okay. So in my starting year, in the year 2000, my cost is $10,850. That is my initial amount. So for A, I'm going to plug in 10,850. Then inside my parentheses, I'm going to have 1 plus R. I'm always going to have a 1, and because it's growth, I'm always going to have a plus. And like I said earlier, your R value is almost always given as a percentage. And what they're telling us is that the cost rises by 5% each year. R is equal to 5%. But here's the thing. You can't plug in 5 into this formula. Okay, it'll make everything crazy. You have to convert this percentage into a decimal. So what you know is 5% is a decimal. All you got to do is move this decimal 2 units to the left. So 5% as a decimal should be 0.05. It's increasing at 5%, so you plug in 0.05 in for R. And then we want this equation to be able to plug in any amount of time that we want. So we'll just call this to the t power. Clean this up a little bit, and your equation should be y is equal to 10,850 times 1 plus 0.05. 1 plus 0.05 is 1.05 raised to the t power. Okay, this is the equation that models a scenario. We can plug in any amount of time and solve for the cost in that given year. Okay, so now what they're asking us is they're asking us specifically about what is the cost in the year 2015. Okay, so what we got to determine is what should I plug in for t if I'm trying to solve for the cost in 2015. My starting year was the year 2000, and if I'm trying to figure out the cost in 2015, I got to figure out how much time has passed. So, once again, my starting year was the year 2000, and my final year, the year I'm trying to solve for, is the year 2015. So I asked myself, how many years passed between 2000 and 2015? That's 15 years, so the value I'm going to plug in for t should be 15. Okay, so once I have that, it just basically becomes a plug and chug. Rewrite your equation exactly as you see it. 10,850 times 1.05 raised to the 15th power because 15 years have passed. So when you're doing this, super important, you account for order of operations. You got to do the exponents first. The first thing you have to do is you got to do 1.05 raised to the 15th power. Use a handy data calculator for you, 1.05 raised to the 15th. You should get this ugly decimal. It'll be something like 2.07892, and it goes on for a while. Okay. So I know it's ugly, but it doesn't really matter. All you're going to do is you're going to take that number and you're going to multiply it by 10,850 times 10,850, and you should get this new y value of y is equal to 22,556. And because we're dealing with money, we can go to 2 decimal places. We'll call it 37 cents. Okay, so we expect the cost in the year 2015 to be about $22,000. Okay, so in comparison, we could do this almost exactly the same equation, even if it's exponential decay. Okay, so here's the big difference though. You'll notice that this equation looks super similar to the one we talked about up here. All the pieces are exactly the same. All the variables mean the exact same thing, but the one difference is if you know you're dealing with exponential decay, it's getting smaller and smaller every time, rather than adding the rate like we did up here, we're going to subtract the rate. So that might be a good important thing to add. If it's growth, you add the rate. Add the rate of increase. If it's decay, if the model's getting smaller and smaller over time, you subtract the rate. So if we look at this example, it says the population of Campbell County, Kentucky has been decreasing at an average rate of 0.3% each year. We know this is exponential decay because the rate is decreasing. The population is going down and down, 0.3% per year. And it says in the year 2000, its population was 88,647. My starting value is 88,647, and it says write an equation to represent the population since 2000. And then after that, it says predict the population in 2010. So first step, let's write the equation. Because we know the population is going down and down, it's going to follow decay. It's going to look like y is equal to a times 1 minus r raised to the t power. So in order to solve this, we just got to figure out what a and r are equal to. I'm still going to have y equals to solve for the number of people. A still represents my starting amount or my initial amount. Okay, in the year 2000, the population is 88,647. That is still my A value, 88,647. In my parentheses, I'm going to have 1 minus my rate of decrease. So I'll have a 1 minus, and just like exponential growth, rate is usually written as a percentage. In this case, it's telling you that R is equal to 0.3%. So got to be super careful here. Cannot plug in 0.3. You'll get a different number. You have to convert this percentage into a decimal. So you have to move this decimal 2 units to the left, and it's going to be a really, really small number. It becomes 0.003. That is the number you have to plug in to this equation, 0.003. And then we want to be able to plug in any amount of time we want, so we'll just call this t as my variable. Clean this up a little bit, and you should get y is equal to 88,647. 1 minus 0.003 should give you something like 0.997. And then I raise this to t power. Okay, this is the equation I'm going to use. That'll help me to solve for any amount of time. But if it asks specifically for the year 2010, I can plug in a value for t. So my starting year was the year 2000, and I want to solve for 2010. I ask myself, how many years have passed? Well, in this case, it would be t is equal to 10. 10 years have passed between 2000 and 2010. So I plug it in. 88,647 times 0.997 raised to the 10th power. Okay, once again, order of operations, super, super important. Got to do the exponents first. 0.997 raised to the 10th. 0.997 raised to the 10th power. You should get something like 0.97041. 0.97040, and it goes on for a while. Whatever this ugly number is, all you got to do is multiply it by 88,647. And you do that, 88,647. And you should get something like y is equal to 86,023. And there's no reason to go to the 10th or the 100th place. This is people. You can't really have a tenth of a person or half a person. So my new population in the year 2010 should be 86,023.